So, hi everyone. In this video, we will learn about irreducible polynomials. So, by now you are familiar with what fx is. Okay, this what is capital F box x is. So let me recall that for you. It is a ring, and this ring have basically all those polynomials uh, whose coefficients are defined over some field. Okay, so we will define what field we can take. So we can take real number field, we can take integer field. Okay, so whatever field we take, all the coefficients will be taken from that field. Okay, so let's say px is that polynomial that belongs to this set. Okay, so when will I say that px is irreducible? If I can't factorize px, if I can't write px in terms of product of other two polynomials, in that case I will say that my px is irreducible. If I am able to find any two polynomial in my set fx whose product is becoming equal to px, then that won't be an irreducible polynomial. That will be a reducible polynomial. So here I have defined that mathematically, that if you take p1x and p2x, two polynomials, and if I am unable to find any two p1 and p2x whose product is becoming equal to px, then that will be my irreducible polynomial. Also, only those polynomials will be called irreducible whose degree is at least 1. Okay, if degree is 0, then that will be a constant term, and I'm not considering that as a polynomial. Okay, I'm not considering that for my irreducibility test. So you have to consider only the polynomial that have a degree at least 1 for it to be irreducible. Okay, so you got what is irreducible and reducible. So let's take an example on it. So here we have x square plus 1 polynomial, and that belongs to f2x. Now what is f2x? What does it mean here, writing that 2 in subscript? Okay, which means that this is a set of all those polynomials whose coefficients are from f2 field, or the field defined over zp, z2, and what elements we have in z2? All the integers from 0 to 2 minus 1, that is 0 to 1. So what integer we have 0 to 1? Only 0 and 1. So the choice of coefficients of the polynomial in this set is 0 and 1 only. So here you can say that coefficient of x square is 1, and this constant term is also 1, and coefficient here x cube is 0. All other degree term have coefficient 0. So none of the other kind of coefficient is appearing here. So this x square plus 1 belongs to this f2x. Okay, so now I want to check, is this reducible or irreducible? Okay, so let's work on it, and let's try to find out its vector. So I have x square plus 1, and I need to find two other polynomials. If I multiply them, I get x square plus 1. Okay, so one term is x square. I need x square in my product. So how can I get x square? By the multiplication of two x's. So 1x must appear here, and 1x must appear here in the polynomials, so that their multiplication will yield us x square. Okay, so their multiplication will yield us x square. Also, I need 1 in the result. So how can we make 1 appear by the multiplication of two polynomials? That means that here should be 1, and here should also be a 1. So by multiplication of 1, I'll get 1 also here. But apart from these two, I'll get some different term also. So let's expand these two terms. If I expand these two polynomials, what I'll get? X square x plus 1. So this is what I get if I multiply these two polynomials. Now this, if I combine these two degree terms, then I will get 1 plus 1 times x, and here I have plus 1 and here I have x square. Now I am not writing it 2, I am writing it 1 plus 1. Why? Because 2 does not belong to the set 0, 1, over which our coefficients of my polynomials are defined. Okay, so but here I am getting 2, so what to do? So whenever you get a number beyond your scope, you take modulo. Okay, so, and our defined set is what? Z2. So it is defined over 2. So whatever you get after the operation, we have to take its modulo with 2. So 1 plus 1 is 2, and if I take its modulo with 2, I'll get 0. Okay, so this is what we. So this is not a normal addition. This is addition under modulo 2, right? Because I have defined my coefficient over set Z2. In Z2, what we do, whatever operation we do, the result is not stated directly. First we take its modulo with 2, right? In case of 0 plus 1, or we are just getting 1, in that case there is no benefit of taking modulo with 2, because that will also yield 1 only. Okay, but if I get number greater than 1, that like 2, I have to take modulo with 2, so that I get to know what is the correct outcome of that. So here I am getting 0, so this whole term get vanished from here, and what I'll get? X square plus 1. So what I can say that x plus 1 times x plus 1 is x square plus 1 here in my this f2x, this f2x ring. Okay, so now I have expressed x square plus 1 as the product of two polynomials. So I can say that this polynomial is not irreducible, it is reducible. This is reducible because I have reduced it into the product of two polynomials. So I hope you got it. Alright, so here I am defining some notions here. So I am defining a set I here. Okay, and what that okay, so what that set I will have. So I am fixing a polynomial px. I am picking a polynomial px from my field fx, from my set of polynomial fx. Okay, from my ring fx. Okay, so if I take a polynomial and I multiply this polynomial with all other polynomials in my set fx. So there are a lot of polynomials in my set of polynomial fx. Okay, there are a lot of polynomials. So I am just picking one particular polynomial, and that is px. And what I am doing after that, I am varying this qx polynomial. This qx is varying. Okay, first I'll take one polynomial from fx, I'll multiply with px, I'll get some polynomial. Then I'll take another polynomial from fx, and I'll keep on multiplying with px. So I'll just fix one polynomial from my fx and keep on multiplying that polynomial with other polynomials, and you'll get different polynomials. The set of all those polynomials will be I, and this have a standard name. It is called ideal generated by px. So this set we have generated using px, right? So we have started with px, and using px I have generated all other polynomials in this set. And how I generated? I just multiplied px with every other polynomial in my fx. Okay. This is another kind of important set. So what kind of polynomials or elements this set will have? So you know what fx is. Fx have all the polynomials, and what I'll do, I divide every element in fx with px. I just fix a px. I just fix a px polynomial from my field, and what I'll do, I'll divide every other polynomial in my fx, and whatever I get, obviously I will get a remainder polynomial. Whenever I am dividing, we are taking remainder because operations are here under modulo. Okay, so we are not taking we are not considering the quotient here, we are considering the remainder. Okay, so when you fix a polynomial px from my field fx, and then what I'll do, I divide every other polynomial with my px, and I will get remainder after that. So the set of all those remainder will be in this set. So set of all those remainders will be denoted by this. So px can be anything. Let's say I took x square plus x plus 1. This is a polynomial. So what I'll do, I divide every other polynomial with that polynomial, and whatever remainders I'm getting, I will store those remainders in a different set, and that set will be this set, fx over px. So you can see for every qx belongs to fx, I'll get a rx, which I get on dividing fx with px. Okay, so rx is the remainder obtained by dividing qx, which is in fx, with px. So what can you say about the degree of terms that will have in this set? Okay, we know that whenever I divide x cube with x square, so I'll get x1. So x1 is less than x2. x1 is less than x2. But we want to take the remainder. What will the degree of remainder? Whenever we divide a number, and whenever you divide a polynomial, let's say we have x cube plus 1, and I'll get x square. So if you divide this polynomial and I'll take the remainder, what will be the remainder of this? Definitely the remainder will have degree less than 2. Right, because let's say if x cube plus 1, I'm dividing it with x square. What will I do? First of all, it is I will divide with x square times 1. I'll get x square here plus 0 here. So 1 minus 0 is 1, and also okay, I'll do multiply with x cube. So I'll get x cube here, and that will be 0. What remainder I got? I got remainder 1 here. Okay, and what is the degree of 1? Degree of 1 is 0, and 0 is less than 2. So every time I divide a polynomial with some other polynomial, then remainder can't have a degree greater than the divisor. Remainder can't have a degree greater than the divisor. You can see, because when we are subtracting the higher degree with the product with the factors of my divisor, so the subtraction will yield a degree less than equal to 2, right? So what I can say that all the polynomials that belong to this set have degree less than the degree of px. So we have chosen px for the division, and we are dividing px with all the other polynomials, and we are collecting the remainder. So all those remainders will have a degree less than the degree of px. So that's what I have written here. The degree of rx, and rx are what? They are the elements of this set. So they have a degree less than the degree of px. I hope you got it. Now there is one more important result. I will not prove it, but it is true. It is known mathematical fact that you know what fx over px. Okay, this is a set of all those polynomials which are remainders that we got by dividing px, by dividing all the polynomials in fx with px. Okay, so I combine this set with two operators, addition. So this is a set basically. Okay, and if I combine this set with two other operators, plus and star, that will become a field. That will become a field. And you know what field is. Field has some axioms. Those axioms should be followed. Okay, so not all kind of px will make it a field. When the px is irreducible, then only this combination will become a field. I'm not providing the proof, but it is true. When you take a irreducible polynomial, that will definitely become a field. It will satisfy the axioms of a field. When the px is not a irreducible polynomial, it is a reducible polynomial, then I can't comment. Then it may be a field, it may not be a field. But when the px is irreducible, it will definitely become a field. Okay. So after each operation in this field, outcome is stored as remainder that we get by dividing with px. Okay. That was the definition of this fx over px. So let's take one example here. So my x square plus x plus 1 is a polynomial that belongs to f2x. So you know what f2x, right? In that we have coefficient from on either 0 or 1. Now x square plus x plus 1 is irreducible. You can try to reduce it, but you won't be able to reduce it because it is irreducible. Okay, so px, this x square plus x plus 1 is irreducible. So what I'll do, this f2x set will have many polynomials, and x square plus x plus 1 is one of those polynomial. What I'll do, I divide all those polynomial with this x square plus x plus 1. What I'll do, I take all the polynomials of f2x and divide them with x square plus x plus 1. So I'll get some different set of polynomial, and all those polynomial will have degree less than 2, because what is the degree of this px, this polynomial? 2. Its degree is 2. So if I'm dividing other polynomials with this polynomial, the remainder will have degree less than this 2, right? So this set will have all those polynomials which have a degree less than 2. So can we think of all the polynomials which are in f2x and have degree less than 2? One can be x, it can be x, it can be 1, it have degree 0, this have degree 1, it also x plus 1, it also have degree 0, degree 1, and it have degree 0, right? So any other polynomial that we can think of? No, we can't think of. These are the only 4 polynomial that we can think of in f2x. Don't say that f5x plus 1 is also a polynomial that have degree 1. You know, because this f2x is defined over f2 field, that is z2 that have coefficient either 0 or 1. If you say that 5x plus 1 is also a polynomial of degree less than 1, but that won't be allowed here, because 5 is a coefficient that we won't allow here. We can have coefficient either 0 or 1. So taking coefficient 0 and 1 and then finding out the polynomial which have degree less than 2, they are only these are the only possibilities. So what this set will have, these elements 0, 1, x plus 1. Okay, so let's take one instance of getting one of these remainder. So in my f2x, I can have a polynomial x square plus 1. Okay, in my f2x, I'm not saying f2x over x square plus 1. I'm not talking about remainders. In f2x, which have all those polynomials, x square plus 1 will be one of those polynomial, right? So if I divide x square plus 1 with x square plus x plus 1, so how will I divide? I'm observing that it will go 1 times this divisor. So 1 times this divisor is x square plus x plus 1. What I'll do now, I'll just subtract them. So what I'll do now, x square plus 1, x square plus x plus 1. I'll subtract them. What I'll get? X square get cancelled, and 1 get cancelled with 1 if I'm subtracting. What I'll get? I got minus x. But minus 1 can't be a coefficient, because we can have coefficient either 0 or 1. Here I am getting minus 1 as a coefficient, minus 1 times x. So what I'll do, I'll just whenever we get negative terms under some modulo, what we do, just add that modulo term. So here we have a modulo defined under 2. So what I'll do, I'd add 2 in the minus 1, and then I'll take modulo with 2. What will I get? 2 minus 1 will be 1. Modulo 2, that will be what? That will be 1 only. So this minus 1 on taking the modulo with 2, under modulo 2, that will be 1 only. So instead of minus x, it will be just x. Okay, so it will be just x. So the remainder I am getting on dividing x square plus 1 with x square plus x plus 1 is x. Now this is the method of dividing the polynomials in theoretically, like this is the long method of division. But what if we want to code this method? We want to write a code of this polynomial division. Then from the programming point of view, there are some observations. So I have written this observation. From the programming point of view, we have some hacks. We have some hacks to achieve this division faster. One thing you can observe that if I take XOR of these two terms, then also I'll achieve the remainder. Okay, just take XOR of x square, that will be 0. XOR of 1 and 1, that will be 0. XOR of 0 and x, XOR of 0 and x, that will be 0. That will be x. Right? You are. I'm assuming that you are aware of XOR operator. Okay, whenever we have same input, same entries, that will yield 0, and whenever we have different, we get some non-zero outcome. And XOR of any number with 0, XOR of any number with 0 is that number only. So if you take XOR of each degree term in the divisor and this x square x plus 1, you will get a remainder also. So this is the one way of achieving the remainder. Also, one more interesting thing here is that what is my divisor here? Divisor is x square plus x plus 1. What is my dividend here? Dividend is x square plus 1. Okay, so dividend is x square plus 1. One observation is that if I replace this x square in my divisor with this x plus 1 is some part of my divisor. If I just replace this x square with x plus 1, then also I can achieve the remainder. Okay, let's replace it and let's see what happens. Instead of, if I replace x square with x plus 1 what it will become? X plus 1 plus 1. This 1 will get cancelled because 1 plus 1 will be 2, and 2 won't be considered because under modulo 2 that will be 0. So what do we get? X only. So we got the remainder by doing this approach. So what exactly I did here is that what we do is that you have the divisor. In the divisor, look for the highest degree term. What is the highest degree term here? X square. So highest degree is what? 2. look for the same degree in my divisor. So can I see x square in my dividend? Yes, x square it is here. So what I'll do, replace this x square with that part of my divisor in which I have removed the highest degree term. So step 1 is look for the highest degree term in the divisor. Let me write it for you. So step 1 is look for the highest degree term in divisor. Okay, here in this our example, the highest degree term was x square. So let's say degrees that highest degree is m. Step 2 is look for x raised to power m, x raised to that highest degree in dividend. If you able to spot it in the dividend, then step 3 will be that replace that x raised to power m with what? In my divisor, remove the highest degree term. Remove the highest degree term. So here in my divisor I have x square. If I remove this x square, what I'll get? X plus 1. So replace this term. So what we are replacing? Replace this term. Replace this with x raised to power m. So look for highest degree in the highest degree term in the divisor and replace it with that part of my divisor which we got by excluding the highest degree term. Okay, so I will get x plus 1 if I exclude the highest degree term here, and that x plus 1 got replaced with x square, and then I'll do the simplification. I will get the remainder. Okay, so you might be thinking that it is working here, but in general, is it true? Does it happen all the time? Actually, it is an observation, and yes, it happens all the time when we have it is a special type of phenomena which happens only this kind of set which is defined, which have filled f2, and we are getting some we are trying to get some remainders here. So for your clarity, so to make you believe that this happens, let me take one more instance. So let's say we have x cube plus 1. So x cube plus 1 will also be in f2x, right? Because f2x have all the polynomial that has coefficient in the range in either 0 or 1. So it have all the coefficient 0 or 1. Here we have constant term 1 and coefficient is 1. So this x cube plus 1 will also be in that f2x, and we have our px, that is x square plus x plus 1. So I want to divide x cube plus 1 with this. So the long method of is that I need the term x cube, so I have to multiply it with x, so I will get x cube plus x square plus x. Now you will either subtract them, then solve for modulo, or just take XOR of them. You will get x square plus x plus 1 and x square plus x plus 1. Now that will go one time with divisor, so you are getting remainder 0 here. So that was the long way of doing this. Now, can I do this observation that we learned here? So, what is the highest degree term in my divisor? That is x square. So, can we support x square in my dividend? Can we support x square? Explicitly, I can't see x square in my dividend. Here I have x cube. Okay, but can I form x square here? Yes. If I write x as x times x square, now I can see x square here. So I spotted the same degree term in my divisor. Now what I'll do, I want to replace this x square with something. And what that will be? Just remove this highest degree term from the divisor. What I got? I got x plus 1. So x plus 1 can be replaced with x square. So let's replace x square with x plus 1. What we will get? X square plus x plus 1. Again I am seeing x square here. Again I can replace that x square with my x plus 1. So let's replace it again. So I replace it x plus 1 plus x plus 1. Now you will see that this one get cancelled by 1. Now by cancelling I mean that when I will add them, I'll get 2, but 2 is not allowed. I have to take modulo with 2, that will be 0, so they get cancelled. Again x by same argument, x will be get cancelled with this x, so what we get 0. So this is working. This way of finding remainder is working. So it is really fast method of finding remainder in our set of polynomials that are defined over field F2. Okay. Yeah. So this was all about irreducible polynomial, and we saw how to find the remainder in a really fast way. So I hope you got it.